Hello, this is Mr. White, and this video is on volumes of solids with known cross-section. Here are the exercises for today. We'll point out that that last section, part D there, is also known as finding volumes of revolution, also known as the disk method. So before we jump into this problem, let's briefly discuss the premise for what we're about to do. Let's say we had some shape just floating out here in space. And let's say that we gave it a little bit of thickness. And let's say that this area, when it was a two-dimensional area, let's say it had an area of A. And as far as how much we thickened it, let's say that it has a thickness of dx. And we recognize dx by now. We understand that it represents some infinitesimal quantity, smaller than any number you can name, but not equal to 0. Now, if I wanted to know the volume in three-dimensional space of this little slice, we would just take the area and multiply it times the infinitesimal thickness. Well, let's say we had some other little area, and we also gave it a thickness. Well, it also is going to have a volume given by the formula a times dx. But we better be clear that the area of this shape is not necessarily the area of this shape. And in fact, they're probably different. So let's call this first area, let's call it A1. And let's call this second area, let's call that one A2. And therefore, the volumes change accordingly. A1 times dx, A2 times dx. So you can probably see where this is going. Let's say we had some third little area. And how about a fourth? And they, of course, have areas of A3 and A4, respectively, and volumes of A3 times dx and A4 times dx, respectively. So even though the area of each little slice is different, we are assuming that the thickness is dx in every single case. Every one of these slices has the same infinitesimal thickness, dx. So this is how we're going to conceptualize three-dimensional volumes, as just an infinite number, an infinite stack of infinitesimal slices. And conceptually, we would get the total volume by adding up all the individual volumes of these little slices. So A3 dx plus A4 dx. And of course, in reality, this would go on quite a bit longer. We'll just say up to A sub n dx. And of course, we notice that the dx is a common factor here. So I could take the dx outside some big parentheses. And inside those parentheses, I could write A1 plus A2 plus A3 all the way up to AN. But this is starting to feel very familiar. That's what sigma was for. And then this is the case where we'd say sigma of A sub I, starting with I equals 1 and ending with I equals n. To get a total volume as accurate as possible, we want there to be as many little slices as possible, so we take the limit as n goes to infinity. That is going to give us our total volume, which we'll call V, and we also recognize that that can be written as an integral, which can be FTC'd and all that great stuff. So when we think of this being on a coordinate system, we'll integrate A, which changes with x value as a function of x. We'll still have that infinitesimal thickness dx in there, and we'll add up these areas from an x value of A to an x value of B. So this is the general formula for finding the volume of solids with a known cross-section, a cross-section whose area can be given by a formula such as A of x. Okay, make sure you know this formula, make sure you understand it. Volume as an integral of A of x, because that is what we're going to be using here. Let's get back to the exercises. Let's move this aside and see what we're up against. Okay, we are to find the volume of a solid on the x interval from 0 to 4, And let's see, we're given an equation here, but let's be clear, this equation is not giving us the area itself. What this equation is giving us is this represents the base of a rectangle with a base to height ratio of 2 to 1. And from all that information, we will come up with an area formula. Let's bring a picture of that function onto the screen. And again, we are operating on the interval between 0 and 4. And over that interval, these vertical line segments represent the base of rectangles coming out of the page, out of the screen. And the rectangles have a base that's twice the height. So given the very 3D nature of this problem, and since I can't draw rectangles coming out of the screen, and let's at least try this perspective view. And again, here are those vertical line segments between x equals 0 and x equals 4. So keeping in mind that 2 to 1 ratio, I'll draw that last rectangle, something kind of like this. Again, I'm trying to visually draw it about twice the base as the height. And that means that that rectangle that I just drew is going to be taller than, let's say, this first rectangle that I'll draw over here. Let's draw, let's say, this middle one in here. Again, at all times, the base is twice the height. So not only is the base growing as you move along the x-axis, but the height is too. So let's draw the rest of those rectangles in here. Something like that. So it's getting a little bit messy here, but we can kind of envision this solid now. And if I try to draw the edges of this three-dimensional solid whose volume I'm trying to find, might look something like this. And if I move it off to the side, again, not the best masterful work of art, but at least it's enough to give us a sense of what we're dealing with here. Okay, so where does all the math fit in? Where does this f of x fit in? Keep in mind that for any given rectangle, and I'm just going to pick one at random here on the screen, let's say this one right here, its base was given by f of x. So let's write f of x there. And its height was in a 2 to 1 ratio, or in a, I guess I should say base to height is in a 2 to 1 ratio. So the height here of that rectangle would be half f of x. And therefore, that's the area that we're seeking to use in that formula, a of x. The area is going to be base times height. And of course, we could abbreviate that as 1/2 f of x squared. So we'll write our integral for volume. Volume equals the integral. We said the interval of x would be from 0 to 4 of a of x dx, which in this case is 1/2. I'm going to go ahead and square our f of x. F of x was x to the 1/3 power, so if I square it, we'll get x to the 2/3 power dx, which will give us, let's see, by anti-derive, 3/10 x to the 5/3, evaluated from 0 to 4. And we're going to need to grab a calculator here pretty soon, but let's go ahead another step or two. That'll give us 3/10, 4 to the 5/3, and then this 0 will just produce a 0, so I don't need to worry about it. And finally, if I want, I could think of that 4 as a 2 squared, which would allow me to write this as 3/10, 2 to the 10/3. Again, we really just need to grab the calculator at this point. Enter in 3/10 times 2 to the 10/3, and we get about 3.024. If we're given units on that, we would say those were units cubed. All right, that is our answer. So I'll put my lazy man's box around that final answer. Something like that. Okay, let's scroll down to part B. Okay, very similar premise here, but this time all those vertical line segments bounded between f of x and the x-axis are now going to represent the hypotenuse of an isosceles right triangle. So that last line segment, for instance, might look something like this coming out of the xy plane. And one of the earlier line segments might look something like that. And let's populate the rest of those isosceles right triangles coming out of the xy plane. And again, something like that. And if I draw the edges, I'm certainly not suggesting that you have to go through this entire process every time, but do whatever you have to do to get a sense of the shapes that we're dealing with. Okay, something like that. Now, as far as the area of these isosceles right triangles, as far as that area formula goes, it's in a bit of a different orientation than we're used to, but let's just draw off to the side an isosceles right triangle with its hypotenuse horizontal. I'm not trying to draw perspective anymore. This is just on the flatness of the screen. So here's the right angle, and here are the 45-degree angles. So interesting to note that if you drop a perpendicular line segment down like this, you get two smaller 45, 90-degree triangles. And let's recall that in our perspective drawing there, that this hypotenuse was represented by this f of x right here. So if this total length here is f of x, then this length, and also this length are half f of x. Now the one we're really concerned with here is that middle one, so I'll go ahead and label that 1/2 f of x to represent this height. And notice that if I draw this rectangle in here, that is the same rectangle we were dealing with back in part A. And so that the triangle that we're dealing with now is clearly half the area of that rectangle from part A. So for this isosceles right triangle, the new a of x formula will be 1/2 of the base f of x times the height 1/2 f of x. So this is going to let us take a great shortcut here. If I scroll back up to part A and look at the calculations we did, notice that where we're at with this isosceles right triangle is we need to just take this integral and put another half in there, multiply by 1/2. And same with every step after it. Everything is just getting multiplied by 1/2. In fact, the entire volume from step B is just half the volume from step A. So rather than just repeat all those steps again, I'm just going to drag this result from the previous part A down to where we're working. Okay, here we are. And we'll just insert a 1/2 in there. So we'll get 3/20, 2 to the 10/3. And on our calculator, I've still got that previous value from part A, so I'm just going to put divide by 2, same as multiplying by 1/2. 1.512. And we'll put a box around that. Okay, hope you're starting to feel comfortable with these. Let's go on down to part C. Same premise once again, but now these vertical line segments represent diameters of semicircles. There we go. There's our volume. Now let's consider how f of x relates to our semicircle and how we're going to get an area equation out of that. Off to the side, I'll draw that semicircle. Again, just in two dimensions now, over here to the left. And once again, this f of x distance over in our perspective sketch is represented right here as the diameter. So we'll make it very clear that that is f of x. Now, the area of a circle we know is pi r squared. And since we're dealing with the semicircle, we'll put a 1/2 right here. And I'll put a little note there just reminding it that that's because it's a semicircle. And now notice the relationship between r in our familiar circle or semicircle equation here. What's the relationship between r and f of x? Well, we see from the sketch that this radius r is equal to half of f of x. So we'll put 1/2 f of x, substitute that in for r. Okay, now I'm going to simplify that as 1/2 times pi over 4, again, pi, and then this 2 down here is being squared because it's inside the parentheses, so pi over 4, f of x squared. And you may be wondering, why don't I combine this 1/2 and pi over 4 to make it pi over 8? Hold on just a second for that. Since this is an expression for area, the volume is what I get when we integrate that from 0 to 4 dx. And what I'm going to very cleverly do is I'm going to pull only the pi over 4, which is a constant, of course, so I can pull it to the outside of the integral. And now I see that here I have the very integral I had way back in part A. That's why I only pulled the pi over 4 out separate and left the 1/2 in there. The 1/2 was part of the integral back in part A. So what that means is I can once again save myself some trouble, save myself some work, go back to part A here. I'm going to grab this evaluation of the integral and let's drag it down to our present work. Okay, and there it is. We'll multiply that times pi over 4. See, that will give us 3 pi over 40 times 2 to the 10^3. We'll bring up the calculator where I've just entered that in, 3 pi over 40 times 2 to the 10^3. And that's about 2.375. .375 units cubed. We'll get rid of that earlier box so I can put a box around this answer. Okay, are you ready for the fourth and final part, part D here? These familiar vertical line segments will now represent the radii of circles. And one thing I should have made explicitly clear in writing this problem is that the centers of these circles will lie on the x-axis, not on the curve itself. So if the centers had lied on the curve itself, we may end up with something that looks kind of like a circle that looks kind of like that at the end. But what I intended and what you'll typically deal with is a center on the x-axis there. Okay, let's draw in some more circles. Okay, wow, look at that. I'm going to admit I was kind of tempted to just erase this clip of the video and redo it so you couldn't see this abomination, but I figured I'll let you go ahead and see that my pictures don't always turn out beautiful either. So we'll end up with a shape that looks something like that. And off to the side, we'll draw a representative circle here. And notice that f of x, this f of x distance, now is the radius of this circle. So when we write area of a circle is pi r squared, in this case, that will be pi times f of x squared. And our volume, of course, will be the integral of that from 0 to 4. So now we're getting the hang of this. If we want to make this look more like our previous integral that we encountered back in part A, we would put a 1/2 in here only because it was present in part A, and we would balance it out with a 2 out here. So if by any chance you haven't watched this video all the way through, you might want to go back and see the earlier part for part A. This integral is something that we've already calculated the value of. So I'm just going to scroll up a little bit this time. We had used that same value back in part C. So here's where we used it in part C. Let's just drag it down. And times the 2 pi will give us 3 pi over 5 times 2 to the 10^3. We'll bring on the calculator, 3 pi over 5 times 2 to the 10^3, and that gives us 18.999. 18.999 units cubed. And this time I'll just put a V up here. V equals 3 pi over 5. You may have noticed I like to put a box around both the exact expression and the decimal expression. So there you have it. And you may have recalled something I mentioned at the outset of the video. I'll point it out once again, that this part D, where f of x represented the radius of a circular cross-section, those are also referred to as volumes of revolution. And the process we just performed here in part D is also called the disk method.